Hello, this is Mr. Gilmore with the 8.3, the Pythagorean Inequalities lesson. So we kind of opened an interesting question back in our 8.2 part 1 lesson on the Pythagorean converse. What we found in the Pythagorean converse was a way to test to see if a triangle is a right triangle. However, the question we want to ask ourselves now is, would it be possible for us to determine if a triangle is acute or obtuse if it's not a right triangle? So what if a squared plus b squared is not equal to c squared? Well, then we obviously know it's not going to be a right triangle based on the Pythagorean converse. But our next question is can we know that the triangle is going to be obtuse or acute if a squared plus b squared is not equal to c squared? Well, the answer is yes, and here's the rough idea. To make a triangle acute, think about taking an acute triangle, taking a right triangle, and we shrink the hypotenuse, leave the legs the same length, but if we shrink the hypotenuse, that means we're going to find that a squared plus b squared is now greater than c squared because our third side got shrunk, right? Which means the value of our hypotenuse is now less than that of the sum of the squares of his legs. So then, if we continue that same thought, so stick with the right triangle, and we take the hypotenuse and we stretch the hypotenuse out just a little bit longer. That means if we leave the legs the same length, that means we now have the c squared value, which is our hypotenuse value, greater than that of a squared plus b squared. So there is a way then to determine if a triangle is an acute or obtuse based on whether or not a squared plus b squared is not equal to c squared. And how it's determined is by looking at, is a squared plus b squared greater than c squared, or is a squared plus b squared less than c squared? So let me introduce you to our first inequality, the Pythagorean inequality A, which the A stands for acute. So let A, B, and C be the lengths of three sides of a triangle. Now again, we're going to let the C value be the greatest of the three sides, so it's going to be A is less than or equal to C, or B, and B is less than or equal to C. So make sure C is one of the greatest values. Then the first of our inequalities for inequality A says this: if a squared plus b squared is greater than c squared, then our triangle ABC is acute. So how are we going to prove this? So let's take a look at our setup of this proof of inequality A. So we're given triangle ABC such that we have let side C be the greatest of the three sides, right? So we're saying that A is less than or equal to C and B is less than or equal to C. But remember, we're also given that a squared plus b squared is greater than c squared. And we're going to prove that that triangle ABC, is acute. In other words, we're going to specifically show that angle C is acute. If we can show that angle C is acute, then we'll know that the rest of the triangle has to be acute as well, which means we'll have an acute triangle. So our strategy actually comes right out of the same playbook that we did with the proof of the Pythagorean converse, and that is to construct a second triangle. Construct triangle RST such that angle T is a right angle, and using our ruler postulate to measure and make measure, that we have side R equal to side A and side S equal to side B. So here is our proof of inequality A. Now, our diagram is the same. We still have triangle ABC. We have triangle RST, this constructed triangle, such that angle T is right, and that we have two sides of one triangle, two sides of the other, and we're going to actually take advantage of those equal sides here in just a moment. Now remember, we're given that side A squared plus side B squared is greater than our third side of our triangle C squared. We're going to prove that angle C must be an acute angle, which then means our triangle must be an acute triangle. So we start off with our given. We're given that a squared plus b squared is greater than c squared, and remember that a is equal to r and that b is equal to s. So we know that we have those two sides of one triangle equal to two sides of the other. Now what we can do is take our relationship there, that inequality of a squared plus b squared greater than c squared. Well, since we know that a is equal to r and b is equal to s, let's replace them. So take a out and put r in, take b out and put s in, which means now we have this relationship of r squared plus s squared is greater than c squared. But we know something about r squared plus s squared, don't we? Because our triangle RST is a right triangle, we can use the Pythagorean theorem to say that r squared plus s squared is equal to t squared. So there's our key step there. Now, since r squared plus s squared is equal to t squared, and r squared plus s squared is greater than c squared, that means with some substitution, we know t squared is greater than c squared. That's what we get in step 4. Taking the square root of both sides, we get t is greater than c, which then means we tap into an old theorem all the way back from first semester, converse hinge. The way this one works, remember, is that if two sides of one triangle are greater than are equal to two sides of another, and the third side of one is greater than the third side of another, then the angle opposite must be the greater angle. So what we can prove is that the measure of angle t is greater than that of measure of angle c. But if angle T was constructed to be a right angle, then angle C must be less than that of a right angle. And what do we call an angle that's less than that of a right angle? That is an acute angle. So angle C is acute by the definition of acute. Thus, we know triangle ABC is an acute triangle. Now let's move on to the Pythagorean inequality O. The O stands for obtuse. Let's now prove that if a squared plus b squared is less than c squared, then our triangle will be an obtuse triangle. So again, what we've done in this case is we've stretched our hypotenuse just a little bit such that a squared plus b squared is now less than c squared. Now, we again are going to take our playbook out of what we saw with our Pythagorean inequality A and also back with our Pythagorean converse. So our setup of inequality O is similar to the first. The only thing that's different then is that a squared plus b squared is now less than c squared. Okay, so we're going to prove that triangle ABC this time is obtuse. So again, we're going to let c be the greater of the three values. So a squared plus b squared is now less than c squared. Let's prove that this is an obtuse triangle. So what we do, let's start by constructing a triangle RST such that angle T again is right and that our side R is equal to side A and that side S is equal to side B. So now let's jump into our proof again. We're given that triangle ABC has the two sides equal to the two sides of RST and that a squared plus b squared is less than c squared. So again, we have that all in our given now. Using the exact same strategy as inequality A, we're going to arrive to a conclusion that angle C is an obtuse angle. Because if we can prove that angle C is obtuse, then it must be an obtuse triangle. So we have now, we're taking in step 1, a squared plus b squared is less than c squared. We can replace side A with R and side B with S again. So we get R squared plus S squared is less than C squared. But again, we know something special about our right triangle RST, the Pythagorean theorem. R squared plus S squared is equal to T squared, which means T squared is going to be less than C squared this time. Taking the square root property, we have T is less than C. And then using converse hinge again, we can say the measure angle T is less than that of angle C. Now, if angle T is a right angle and it's less than that of angle C, that means angle C must be greater than that of a right angle. That makes it an obtuse angle by definition, which then means we have proven the inequality O. It's a very similar strategy to that of inequality A. Let's put these two theorems into practice just to test how we can actually find whether or not a triangle is a right triangle, an acute triangle, or an obtuse triangle based on the ABC values. So in our first example, a triangle has side lengths of 60, 91, and 108. Let's classify it as either right, acute, or obtuse. Now again, we need to let our C value be the greatest of the three sides. So we have A and B being 60 and 91, and we'll let C be 108. So what we're testing is 60 squared plus 91 squared and 108 squared. We're going to test to see what is the relationship between these expressions. Is that going to be less than, equal to, or greater than? And we'll figure out then, based on that information, whether it's right, acute, or obtuse. So 60 squared is 3,600. 91 squared is 8,281. And 108 squared is 11,664. Let's then add these two together. We get 11,881. And on the right-hand side, 11,664. That means we have greater than symbol, okay? That 11,881 is greater than 11,664. That means our a squared plus b squared is greater than that. What that leads us then to conclude is that our triangle is acute. When the sum of our two legs is greater, that must make the angle smaller between them, so it must be an acute triangle. Now let's move on to our second example. Triangle has side lengths of 4, 2, and 3. Classify it as right, acute, or obtuse. So again, same story. We're going to assign our A, B, and C values, test them, and check to see what type of triangle this will be. Now, the one mistake the students will make is they'll just read through the three numbers and think that the C value will go on the very last number. That is incorrect. Remember, we always assign the C value to the largest number. So 4 is going to be our C value, and then we'll assign A and B to our sides of 2 and 3. So I'm doing 2 squared plus 3 squared, and we're testing that against 4 squared, right? What's going to be the sign between them? So let's simplify. 2 squared is 4, 3 squared is 9, 4 squared is 16. We again are going to add those 4 and 9 together. We get 13. That is less than 16, which means if it's less than, we can conclude that this triangle must be obtuse, because what we've done is now saying the sum of the legs is less than the hypotenuse. So we stretch the hypotenuse, making it the angle opposite greater than that of a right angle, making then that an obtuse triangle. Now we're here at the end of our lesson with 8.3, the Pythagorean inequalities. You'll be seeing the use of these two inequalities on the worksheet, as well as you being asked to repeat the proofs that you saw here in the slides. If you do have any questions on that worksheet, do not hesitate to email me with that. Be good and do good.